Hi everyone! Good evening! So, in today's video, I'll walk you through sa atong discussion about ADCs or analog to digital converters. We'll briefly explore unsa ang ADCs, nganong importante sila, how they work, and their rules in our everyday lives. So, by the end of this, you'll have a solid understanding of this essential concept in electronics. So, let's get started. What is ADC? To begin with, ADC stands for analog to digital conversion. As what you can see here, analog signal represents sine wave, while ang ato digital signals represent the square waves. Kay jumping between set values of zeros and ones. So, why is ADC important? So now, why do we need ADCs? Well, most of the signals around us are analog in nature. For instance, like the temperature, pressure, sound, and velocity. So these are all examples of analog signals. However, digital devices like computers or smartphones can only process digital signals. So, to bridge the gap between the analog world and the digital technology, we use the ADCs. For example, think about using a smartphone to stream music. So, ang music file ani kay digit bit stream. So, para aron madungog nimo sa speaker, kini convert sa ato ang electrical signal. So, when you speak sad sa imong phone's microphone, so it captures your voice as an analog signal, which is interact with ADC more often than we realize. Now, we are now sa differences sa analog o sa digital signals. So, analog versus digital signals. So, let's dive deeper into analog and digital signals. So, analog signals kay continuous siya, meaning mo change siya smoothly over time, like waves. So, ang example ani kay is ang human voice or radio voice. Digital signals, on the other hand, kay discrete. So, they switch between set values, just like sa light bulb that can either be on or off. So, they're easier for computers to process tungod kay nagamit og binary code, the O's and ones. So, I have here the key differences between analog and digital signals. To summarize the differences, so can I ask you if have you ever wondered why our technology shifted from things like old radios or vinyl records to computers and smartphones? So here, type analog signals are smooth and continuous, while atong digital signals jump between discrete values. So another one, the representation, ang analog signals represent real-world phenomena like sound or light. So while ang atong digital signals pod kay represented in binary format, the O's and ones. So in noise handling, ang analog signals kay sensitive siya sa noise. So they can easily get distorted. So here po dakto ang digital signals kay mas resistant tungod kay it's easier to distinguish between A0 and A1. Sa transmission efficiency, ang analog signals kay lost quality over long distances and need more bandwidth. So, here sa atong digital signals po kay pwede makompress og mas better during the transmission. So for our next slide, as what you can see, we have here the block diagram of ADC. So let's understand how ADC works with the help of this block diagram. So it's the process of converting an analog signal into a digital one involves several steps. The analog signal is first applied to the sample block where it is sampled at a specific sampling frequency. The sample amplitude value is maintained and held in the whole block. It is an analog value. The hold sample is quantized into discrete value by the quantized block. At last, the encoder converts the discrete amplitude into a binary number. So first, sampling, and then holding, quantization, and lastly, the encoding. So first, the sample. Ang pinakaunang step mao ang pagkuha og samples sa analog signal nga specific nga time interval. So, ang samples kay adunay continuous amplitude pero discrete in time. So, next is the hold. So, ang sampled value kay gi-hold constant hangtod sa sunod nga sample. So, this ensures nga dili mausab ang value during the process. So, next, ang quantize. So, sa kini nga step, ang continuous amplitude sa sample kay i-convert ngadto sa discrete amplitude levels nga maghimo sa signal nga suitable for digital processing. Next or last, the encoder. So, here, ang quantized signal kay i-convert ngadto sa binary number since digital devices work with binary data. So, kini nga step crucial para ma-process ang signal. So, the entire process takes place in a matter of microseconds. So, nga naghatag og abilidad nga i-convert og i-process ang signal halos instantaneously. So, here in this slide, the key principles of analog to digital conversion. So, let's break down the key principle of ADC, so each to be explained by my groupmates. So, first, Ms. Hontilia will start with a sampling rate, introducing the Nyquist-Shannon theorem, which determines sa minimum rate nga kinahanglan i-sample ang analog signal aron ma-preserve ang tanan nga information. So, sa next would be Ms. Laurito. She will discuss the quantization and step size. So, she will explain how the continuous amplitude of an analog signal is converted into discrete levels. So, next will be Mr. Tayong. Mr. Tayong will walk us through sa solving sa ADC conversion problem. So, highlighting the practical challenges in ensuring accurate conversion. So, next will be Ms. Guud. She will cover quantization error, so which arises when the actual analog value is rounded off during the quantization process, so affecting the accuracy of the digital signal. And next would be Ms. Tranghea. So, Ms. Tranghea will discuss the types of ADC architectures and ADC performance metrics. So, she will explain the different methods of ADC design and how to evaluate their performance. So, lastly, Ms. Pilapil. Ms. Pilapil will conclude with noise and errors in ADCs. So, she will discuss how noise can affect the conversion process of exploring applications and case studies to show real-world examples of ADC use. So, that's just a brief overview of ADCs and their significance in connecting the analog world to digital devices by converting real-world signals into digital data. So, ADCs play a vital role in electronics. So, gikan sa simple nga smartphones hangtod sa complex nga industrial machinery. So, thank you for listening, and let's move forward sa kang Ms. Hontilia's nga discussion.
Good day everyone, I am Henny Jane Hontelia, and today I am going to discuss the sampling rate. So what is sampling rate? So a sampling rate, an ADC takes a continuous analog signal and converts it to a discrete digital signal by taking samples that represents the signal's amplitude at specific points in time. So kanina ang sampling rate is, we will take or magkuha ta og continuous analog signal and we will convert it ato siyang i-transform into digital signal sa pamaagi nga magkuha ta sa mga samples that represents the signal's amplitude in a given span of time. So kaning sampling rate or the sample rate or sampling rate is the number of samples taken per second. So next, the units for sample rate are samples per second or hertz. The two are equivalent, so the same ra sila, since the hertz is equal to the reciprocal per second, or hertz is equals to 1 over s, or s raised to the power of -1. Hertz is the unit for frequency, and the sample rate is sometimes referred to as the sampling frequency. Sample rate and sampling frequency represents the same value, so same ra sila. This simply means how many samples or data points it takes within a second. The more samples the ADC takes, the higher frequency it can handle. So the more nga daghan imong kuhaon nga sample, the more siya closely sa original nga file para sa imuhang digital file nga gi-convert. So the higher the sampling rate, mas accurate ang digital version sa imuhang signal. However, kung sobrang kataas ra sad siya, ang sample rate is magkinahanglan siya og daghan nga storage space para sa imuhang digital file. So this is one important equation you need to know about sampling rate, and that is Fs, or your sample rate or frequency, equals to 1 over your period of time. So we have here an example. So if the sampling period is 50 millisecond, the sample rate is, so we have here the formula, and that is sample rate is equals to 1 over the time, which is, we have 50 millisecond, and if we convert it to second, that would be 0.05. So calculate, that would be 20 hertz or 20 samples per second. So in this case, the sampling rate is high enough because the frequency of the original analog signal is much lower than the Nyquist rate of 10 hertz. Therefore, 20 hertz is more than adequate for accurate signal reconstruction. That would be all for sampling rate. So the main point of sampling rate tarajud is you will convert the analog to digital in a way that you will get the sample taken per second.
Good day everyone, my name is Simena Nicole Laurito, and I will be discussing a key concept of analog to digital conversion, which is quantization and step size. So what is quantization? Quantization is the process of mapping a continuous range of analog input values to a set of discrete levels. So when we say continuous, it means it changes over time and have different values at different time intervals, and it may or may not be a whole number. So by mapping it to a set of discrete levels, its value will change in accordance of its discrete levels. So the digitization of analog signals involves the rounding off of the values which are approximately equal to the analog values. The method of sampling chooses a few points on the analog signal, which was discussed by Honey Jane, and then these points are joined to round off the value to a near stabilized value. So after atong magbutang nag few points sa analog signal, these points are joined para i-round off sa yung near stabilized value. So for example, its value is 4.8. So we have to round it off to 5. So to further understand quantization, we have here some illustrations. So the analog to digital converters perform this type of function to create a series of digital values out of the given analog signal. So the following figure represents an analog signal, kanang wave sa graph. This signal, to get converted into digital, has to undergo sampling and quantizing. So sampling includes choosing a few points to the analog signal, which is shown sa ikaduha na picture. Then we split the amplitude scale into 8 discrete levels. At every sampled point, our measurements have to stick to one of these discrete levels. So, since ni-stick na siya sa discrete levels, meaning kay na-round off na ang iyahang value to its nearest whole number. Then, the following figure shows the resultant quantized signal, which is the digital form for the given analog signal. So, after ma-round off, muna na siya ang iyahang digital form sa katong given na analog signal. This is also called a staircase waveform in its accordance with its shape, since more siya stairs or hagdanan. Then, here we have its bit depth, 3. So, the number of levels would be 8, since number of levels, iyang formula kay 2 raised to the power of the bit depth. So, 8 levels siya, meaning iyang horizontal lines na diha i-map ang digital values. So, those horizontal broken lines are called the levels. So, both sampling and quantization result in the loss of information. So, this loss of information is called quantization error, which will be discussed later. So, the quality of a quantizer output depends upon the number of quantization levels used. So, ang quality sa output kay magkadepende sa iyahang bit, yung bit depth. So, the discrete amplitudes of the quantized output are called as representation levels. So, for example, this one has 8 representation levels or reconstruction levels. The spacing between the two adjacent representation levels is called a quantum or step size. So, I will discuss step size later. So, here we can compare our original analog signal to the discrete digital signal, where we applied having the bit depth of 3 and then map its digital values to our number of levels. So, this is an illustration of digitally approximating a continuous sine wave with different resolutions. So, as you can see, here we have different lines. So, the green line is our analog signal. So, here we have other lines, color red, blue, and yellow. These are discrete digital signal. However, lahi silang shapes because lahi po ang ilahang bit depth. So, the more magkadako ayang bit depth, the more na ma-close siya sa original analog signal. So, I will discuss more about that later. So, what is step size? Step size or quantization interval refers to the smallest voltage difference that the ADC can distinguish between two adjacent digital output values. It is the voltage difference represented by one least significant bit LSB of the ADC. So here we have a formula. So step size equals V maximum minus V minimum, where V maximum is the maximum voltage and V minimum is the minimum input of the voltage that the ADC can handle. So N is the number of bits used by the ADC or our resolution. So step size and resolution. Resolution refers to the number of bits the ADC uses to represent the analog signal. It determines how many distinct digital values, quantization levels, the ADC can produce. So here we have our formula for the resolution levels. That is 2 raised to the power of n, where n is the number of bits. Higher resolution or more bits leads to more quantization levels, which reduces the step size, leading to more precise digital representations of the analog signal. So, just like what I've shown na illustration ganina. So, the more ayang step size, the more na magkadol iyahang precision sa original analog signal. And if less ang iyahang bits, then less pod ang iyahang resolution. An example of a very low resolution is the red digital signal because its values is far from the analog signal. So the more its bits, the more its representation levels or reconstruction levels. So the more reconstruction levels, the more we can plot the digital values nearly to our original analog signal, which is why the higher resolution leads to more quantization levels. So here we have a sample problem. So you have a 4-bit analog to digital converter ADC that can handle an input voltage range of 0 volts to 10 volts. So the problems are: what is the step size of the ADC? Then how many quantization levels does the ADC have? Then if the input analog voltage is 6.3 volts, to which quantization level will it be mapped? So the first problem is, what is the step size of the ADC? Given by 4 bits and 0 volts to 10 volts, so the solution of this is to apply the step size formula, which is Vmax minus Vmin over 2 raised to the power of n. So n is our bits. Then Vmax is our maximum voltage, which is 10 volts, and our V minimum is 0 volts. So step size equals 10 volts minus 0 volts over 2 raised to the power of 4, since our bits is 4. So 10 minus 0 equals 10. Then 2 raised to the power of 4 is equals to 16. So 10 volts over 16 equals 0.625 volts. So next problem is, how many quantization levels does the ADC have? So if we remember, our quantization levels formula is 2 raised to the power of n. So 2 raised to the power of 4 is 16. Therefore, there are 16 quantization levels. The next problem, if the input analog voltage is 6.3 volts, to which quantization level will it be mapped? So solution, here we have our formula, level equals input voltage over the step size. So level equals our input voltage, which is 6.3 volts. So 6.3 volts over our step size, 0.625 volts. So i-divide na, it will result to 10.08. Since the ADC runs to the nearest available level, 6.3 volts will be mapped to level 10. Since 10.08 man siya. So i-round na nato to its nearest available level, it would be level 10. So the corresponding digital output for level 10. So pila man ihang quantized voltage. So quantized voltage equals to level times step size. Since ato ang 6.3 volts will be mapped to level 10, so 10 times 0.625 volts will be equals to 6.25 volts. That is our quantized voltage. The next slide, here we have our graph sa atong problem. As you can see, if atong iphon ang number of stairs sa ato ang quantized wave, na siya'y 16 levels since our bit is 4. So 2 raised to the power of 4 is 16. Therefore, we have 16 levels. So nag-start siya sa 0 since ato ang ADC has an input voltage range of 0 to 10 volts. So makita ra na sa left side. And this shows the measurement of voltage sa time. So this is the analog sine wave and quantized wave of a 4-bit ADC. So that's all for quantization and step size. Thank you.
So hello guys. Today I'll be discussing about analog to digital conversion. So gidiscuss ako makauban ang pag-convert sa analog signal padung sa digital signal. But ako i-discuss karon is unsaon niya pagkahitabo. Like unsa ang hardware atong gigamit para mabuhat na siya nga conversion or giunsa na pagbuhat sa atong mga device pag-convert nila. So, we'll start by unsay kalahian sa analog ug digital signals. So, gisulti na ning Miss Tamayo, ang analog is continuous and then ang digital is discrete. 0 and 1 ra. So, mao ni example sa analog signal, guys. So, continuous ra siya. So, for example, natay potentiometer diri nga nag-connect sa 5 volts. So, if i-wipe ta ni ang wiper sa potentiometer, is ang voltage na to is mag-usab-usab siya between 5 to 0 volts. So, any value ana is makuha sa ato ang analog signal. Wherein sa digital signal, para makuha ta na ang effect, murag ka ng inana ang effect. Bisag asa siya kay makuha na to ang value. Kay magbuhat patag ka ng murag voltage divider nga circuit or network. So, ari is same ra man nig resistance tanan. So, ang voltage nato is i-divide ra nato kung sa ato ang resistor. So, para makuha nato ang voltage drop each resistor. So, natay voltage drop nga 4, 3, 2, ug 1. So, para makuha nato tong effect is wipe nimo sa potentiometer or kaning ato ang circuit kay mo switch ra siya kanang step. So, for example, if gikan ta sa 0 volts, then niari ta sa 1 volt. So, mo step siya 1. Lahos ra siya 1 ha. Then, if ari na sa 2 volts, is mo step na sa siya pataas. Then, hangtod sa 5 volts. Then, pabalik if gikan ta sa 5 volts. So, if nakabantay mo sa analog is straight ra jud siya. So, any value ana is makuha niya. Wherein sa digital, kailangan pa nato magbuhat og voltage divider para makuha nato ang murag hapit-hapit niya nga effect, but dili pa jud ni siya mao. Kay sa makita ninyo is makuha lagi niya ang value sa from 1, 2, 3 ug 5 volts. But, in between ana is dili na niya makuha. So, dili siya kakuhag value in between sa 0 ug 1. Dili siya kakuhag value in between 1 ug 2. So, mo na ang kalahian nila. So, sa digital is, mura ra gyapon siya if magbuhat og voltage divider, mura ra gyapon siya on ug off. So, if nimo siya, if ari ka mag-base sa 1 ug 0, kay on siya if imong i-swipe diri sa 1, then ma-off siya if imong ibalik diri sa 0. So, same ra gihapon diri. So, para makuha ta ning effect is natay gamiton nga. So, natay mga gamiton nga analog to digital converters nga device. So, para ang kaning analog is himuon natong inani digital. So, magamit ang analog to digital converters. So, unsaan man na. So, daghan klase-klase sa analog to digital converters. But, tanan ana is nag-base jud ani nga component, which is comparator. So, unsa man ning comparator? So a comparator compares two input voltages and outputs a binary signal, indicating which is larger. If the non-inverting, so kaning positive V voltage reference is greater than the inverting input, so kani Vi, which is our voltage input, the output goes high. If the inverting input is greater than the output goes low. So if ang kaning input is greater than our reference is mo output siya high. But if ang input is greater than our non-inverting, low iyang i-output. So unsa gito ang kanang kuan gali ang digital signal? Discrete raman to siya sa which is binary. So maong gamit kining comparator sa pag-convert sa digital to analog is analog to digital, sorry. Sa pag-convert sa analog to digital kay ang voltages or ang input analog voltage na to kay output niya binary. So mahimo na dayon siya digital signal or digital voltage. So an ADC or analog to digital converter using comparators works by comparing an analog input voltage to a reference voltage. Comparators generate a digital signal based on the comparison, with each output indicating whether the input is above or below a threshold. A priority encoder then converts the comparator outputs into a binary value. So mao na kanang i-convert ta niya into binary or digital signal. So mao ni ang basic nga kanang comparator circuit. So for example, if mag-convert ta og 1 bit, so 1 bit ato ang i-convert is usa ra man jud na. So dita magamit sa og priority encoder kay kaning priority encoder is sa mga more than one ni siya nga kanang comparator circuit or ADC converters. So for example, ani nga circuit is natay comparator, then natay voltage reference. So ang voltage reference nato is ibutang nato og voltage divider circuit. So for example, natay 5 volts diri. Ang voltage diri is V over 2. So 2.5. So nganong V over 2 man? Kay ang resistance na to is same ra sila. R1 na to is equal to R2 ani nga voltage divider. So meaning ang voltage drop dire is half sa VCC or sa voltage total nato. Dayan ang atong voltage reference kay gi-connect nato dire sa voltage drop sa R1. Then if mag-input ta for example, if mag-input ta og 3 volts. So if mag-input tag 3 volts, i-compare dayon na niya sa comparator. If ang input nato kay mas dako sa voltage reference, ma-output siya 1. If dili kay mo output siya og 0. So for example, so naatay voltage diri nga 5 volts. Then naatay voltage drop diri nga 2.5. Then atong voltage reference diri is 2.5. 0.5. Then if mag-input ta og 3 volts, so ato 3 volts, then i-compare na niya. Since mas dako man atong voltage input kaysa sa voltage reference, mag-output na siya og 1. But if atong voltage voltage input is lower than, so for example 2 ra atong voltage input, mag-output na siya og 0. So inana ra ang basic comparator circuit. Inana niya pag-convert ang analog input, so mo ni analog voltage input, into a 1-bit binary signal. So example, if magamit na tag priority code encoder, so 2-bit na atong kanang example, 2-bit analog to digital converter circuit. So for example diri is naatay voltage divider gihapon, naatay voltage input, then naatay comparators, and then naatay 2-bit priority encoder. So ang i-output ani is 2-bit output. So binary ang i-output ani, kay digital man. So since natay 4 volts nga kanang voltage reference, ari sa kanang voltage divider nato is natay 3 volts, 2 volts o 1 volts. So nganong nainana man na? It's because kay ang 4 volts nato is naa siya sa voltage divider. Then since ang resistance nato is same value ra, so si atong voltage is i-divide ra nato into 4. So ang voltage drop each resistor kay 1 volt. So mga na, pag agi niya og resistor ni 3 volts na lang, pag agi niya og resistor 2 volts na lang, 1 volt, then 0 volt. So ari is same gihapon comparator. But nganong tulo ka comparator nya duha ra i-output diri. So kani is para makuha nato, for example 2-bit atong gikuha. So sa 2-bit is para makuha nato ang pila ka comparators ang kailangan, depende sa bit, is i-raise to the power nato siya. Raise to the power, 2 raised to the power of pila ka bit, minus 1. So 2 raised to the power of 2 is 4. Minus 1 equals to 3. So mao na tulo ka comparators atong gigamit. Then for example, pila man ka buok gamiton nato if kanang ganahan ta i-convert ang atong analog signal into an 8-bit digital signal. So guys, kanang mas magkadako ang bit sa kanang guys, mas magkadako ang resolution sa ato ang analog to digital, kay mas maka accurate yung result. So for example, 8-bit is 256. 256 minus 1 equals to 255. So ina nakadaghan ang ato ang gamiton nga comparators if 8-bit ato ang i-convert. So karon if sa 2-bit kay mag-convert ta ha. So for example naatay 1 volt. So inanion pagana sa 2-bit analog to digital converter circuit. So naatay 1 volt. So i-compare na niya sa ato ang comparator. So i-compare niya sa 3 volts. So mas dako ba ang 1 kaysa sa 3? So dili. So ang output ani diri is 0. Then ari mas gamay gihapon sa 2. So 0. Then ari sa 1 volts i-compare niya since equal raman. So 0 iyang output kay mo 1 ra ni if greater than. So unsa may output diri sa atong priority encoder? 2-bit priority encoder. So since 0 man ni tanan, output there is 0, 0. But what if mag-input tag 3 volts? So 3 volts. So ang mahitabo is i-compare na niya tanan. So mas dako ba ang 3 kaysa sa 3? So same ra sila. False. And then so karon ang 3 is mas dako sa 2 volts. So 3 volts niya. Voltage ni tanan natong i-compare. Voltage ni sa analog signal na to nga gi-input. So mas dako siya 1 ang output sa atong comparator. Dako gihapon siya sa 1. 1 iya output. So unsa na may ma-output diri? So ari sa priority encoder, i-prioritize niya ang most significant nga or pinakataas nga value sa kuan. So for example, ang gi-compare nato diri is 2 volts. So mao ni yang unahon kay ang 2 volts mas dako man sa 1 volt. So for example, if 1 ni ang kaning sa 3, kay mao ni yang unahon kay ang 3 volts mas dako man sa 2 volts. So mao ni iyang i-read. So pila man ang binary value aning 2 volts? Sa 2 ra ay dili 2 volts. So ang binary value sa 2 is 1 and 0. So mao nay 2 volts. So ang mogawas dito is 2. So mao nay output sa ato ang for example computer. Mao nay i-output niya. So mao to siya sa 2-bit analog to digital converter circuit. So mao ni output. So if maghatag tag 1 volt dito, kato 000 iya output. If maghatag tag 2 volts, 1 so 1 iya output. Then if 3 volts kay kato 2 iya output katong gi-example nako ganina. Then If 4 kay kuan 3 iyang output. So nganong gi-extra naman after na 1? Kay tungod lagi ang i-read ra sa atong priority encoder is ang highest ra nga value. So ari kaning 1 dire is naman ni siya sa 3 volts. So wala na siya pakialam sa naa dire sa uban. Kay mas dako man ang 3 kaysa sa 1, 2 ug 0. So mao na gi-output ra niya lahos ang 1 1 kay ang value sa 3 is 1 1 man. So another example is ang kaning 3-bit analog to digital converter circuit. So nganong na 3.5 naman ang voltage drop dire? Then na 0.5 dire. So magamit gihapon ta sa atong gigamit kanina since 4 volts ra atong kuan. I-divide na to siya kung pila ka resistor ang naa dire. Kay since same value ra man ang kuan, ang atong resistor. So ang voltage drop niya is same ra sa tanang kuan resistor. So gi-divide ra nato og pila man 1 2 3 4 5 6 7 8. So mao na nakakuha tag 0.5 nga voltage drop every resistor. So if kanang for example, ari sa kanang kuan analog to digital nga circuit is same ra man jud na silang value ang resistor tanan. But if makita mong circuit nga kanang kuan kanang dili same og resistance, then pangitaon ninyong voltage drop kay magamit ra mo kanang kuan formula sa katong voltage divider. So voltage total is equals to the, for example, pangitaon ninyong voltage drop sa voltage drop niha. Voltage drop sa first resistor, so R1 over the R total multiplied by, so i-multiplied nimo ang result sa voltage total. So inana ra if kanang kuan gusto mo magkuha sa voltage drop. So not related ra na dire but basing magamit ninyo. So ari sa analog kuan input signal is for example mag kuan tag 3 volts ay 4 lang 4. Ay dili data ka kag 4. 3. Makuha na tag 4 mo 1 ra ni siya tanan. But ari lang ta sa 3. So since ang 3 is mas gamay siya sa 3.5, mas 0 ni dire. Then 0 gihapon ni dire kay equal ra sila. Then mo 1 na ni dire gikan dira sa 2.5 padong sa 0. But since ang 2.5 may kinadak-an nato, i-convert na niya lahos. So unsaan man pag-convert? So i-convert ra na niya og pilay kuan binary value aning 2.5. So i-round up na niya mahimo ning 3. So pila may binary value sa 3? So 0, 1, 1. So mao na hatag sa ato ang output nga digital output nato. So for example, ang kuan ang analog is continuous value ra ba? So dili ra ta pwede makabutang og kanang 3 ra. So maglahi-lahi jud na iyang value. So dili baya madungan niya og kanang process tanan. So napa jud na laing circuit diri. So napa na laing circuit diri. Ngamo kupot sa analog values nato. So mao ni sila gitawag nga sample and hold. So sample and hold na dira. So while gi-process pa niya nga analog kuan value, i-hold sa niyang laing value. So mag-output na dira, then after ana is lahi na sad nga value, then i-output na sad na himuon na sad niyang digital, then hangtod kuan mahuman. So for example, natay sensor. So for example, natay ka ng flex sensor. So, pasensya lang akong drawing. So, i-connect nato og voltage divider. So, maaning voltage. Then, maaning ground diri. So, since nagkuan ta, kanang ang sensor nga atong gigamit is analog iyang output kay ang voltage diri nga part kay ma-change ang voltage drop diri nga part if a fold taning flex sensor. Kay if a fold taning kuan flex sensor is mausab man iya resistance pagkadako man, so ang voltage drop diri sa kuan babaw is magkadako sad sa first resistor kay ma-zero naman ni diri lahos. So i-process na niya. So for example, if kuan ta na flip ta na o fold ta na is mausab ato ang kuan value into 1. So i-process na niyang 1 then gi-flip na sad nato na usab iya value into kuan 2.1 volts. So i-process ani niyang 1 kung pilay value ani. So ang value aning 1 is so 1 ra ang value aning 1, so 0 0 0 0 1. Then after ana na process na nato. Ang kanina sang 2.1 ang iyang kuan butang diri input. So 2.1. So hangtod kuan maundang ra ni if wala tay gibuhat. So if wala na to gi-fold, magsige ra nag 2.1 dira. So if wala na nato gi-on sa dira. So ang kuan ana is ang graph ana if wala na nato gi ilabtan is mag-ana na lang na siya. Dayon, So mao na to ang 3-bit analog. So kanirang 2-bit ug 3-bit akong gi-example kay maura man ni ang gamay. If magkuan ta 4-bit kay mapun-an na sad ato ang comparators. Madaghan na sad diso na explain. But daghag lahi-lahi nga paagi sa kanang pag-convert guys. So ang kaning paagi sa pag-convert is mao ni siya ang flash ADC conversion. So mao ni siya ang pinakapaspas nga type sa pag-convert sa analog to digital. But mao lang sad ni ang pinaka gamay og resolution. Kay magkadako atong resolution, magkadaghan man ang comparators atong gamiton. So nailaing mga kanang kuan styles nga kuan analog to digital or lahi-lahi nga model like naatay ka ng kuan integrator or naatay kuan successive approximation nga analog to digital conversion, which is mao sa gigamit sa atong Arduino nga microcontroller. But same ra gihapon silang output guys. Pero if kuan jud kay mas accurate jud ni ang flash, mas paspas then mas accurate, but gamay lang og resolution. So ang katong kuan, ang katong successive is accurate sad siya and dako og resolution. But medyo mas hinay lang siya i-compare sa flash, which is kani nga kuan type sa pag-convert sa analog to digital. So mao ni ang output niya sa 3-bit. So sa akong gisulti ganina, if magkuan kag 0 to 5, 1 ra imong output. So 1 ra imong output. Then if 0 to 1.5 kay 2, then hangtod 4. So mao na yung mga binary outputs. So binary is digital outputs niya. So ADC practical example. So magbuhat ko practical example ninyo guys ha. So na-mention man ako nga si Arduino is naa siya ay analog to digital converter. So suwayan nato if unsaon jud siya pag-convert sa analog to digital. So for example, if naa kay sensor is ang dawaton ra ba sa sensor depende sa sensor nimo kay if kanang mga kuan lang PIR kay modawat ra man na siya mohatag ra man na siya digital inputs. But if like kuan pareha atong ganina kanang nagamit ka og flex sensor is mohatag siya analog inputs. Or for example, magamit ka og microphone is siya ihatag is digital by analog ra ba? Kay ang sound is i-convert niya into electricity. So dili ka nang kuan if mo kanta ka sa mic kay or nakaistorya sa mic kay dili na niya i-convert into digital kay ang digital is kuan 0 ug 1 ra man. So lahos pa na si analog then i-digital dayon. So, hatagan ta mag example ha. So, ari sa kuan, Tinkercad, mag-suway ta. So, for example, kuan lang tag basic, magamit lang tag potentiometer. Then, ibutang na tog Arduino. So, ibutang na tog 5 volts ang first terminal. Then ang wiper ibutang nato sa analog. So ang kani nga mga pins sa Arduino guys is analog jud ni siya. Si Arduino is modawat siya analog up to modawat ni siya 10-bit analog signal. So sa kaganina is resolution ganina is example nako is 3-bit raman to, but si Arduino is modawat siya up to 10-bit. Then sa ground dayon eh. So i-code na to siya kadiyot. So since nagamit tag analog, okay na ta di mag pin mode guys. But okay ra sad mag pin mode mo, i-set ninyo as input. Mag serial begin lang ta para ma-monitor na to siya sa serial monitor. So i-print na lang nato lahos. Analog read. So basahon niya ang reading sa atong potentiometer. Then unsa siya, asa siya dapit nga pin. So pin 0. Then mag-print line lang ta para mo new line siya after print sa. So if start na nato, so mapansin ninyo is nag-output siya og 1023. So nga naman na, because gi-convert niya ang analog reading. So analog man kay if iswipe ta ni, ang voltage nato is mausab. So dili ta makaingon nga high ra or low. Mausab ihang resistance which is mausab iya resistance is mausab iya voltage. So mao nang analog nato inputs continuous nga pag-usab sa voltage. So mao na iyang gi-output is kani. Unsa man ni? So mao ni akong sa example ganina is mao ni ang result sa ato ang pag-convert. So binary ni siya but gi-convert na into decimal sa ato ang computer para mas dali na to masabtan. So up to kuan ni siya 1023. Kay nganong 1023 man? Kay si Arduino is muhatag lagi siya up to 10-bit. So ang kanang decimal value sa 10-bit is kuan 1023. 1024 ta to. But since ang binary magsugod sa 0, mao nang 1023. So tan-aw na to if so ma-change jud siya hangtod 0. So mao na pwede na ta makagamit og voltage from 0 to 5 volts. So dili na kanang 0505 ra atong magamit. So tan-aw na to ang iyang wave kung gi-convert ba jud niya ang analog wave into a digital. So tan-aw na to. So if nakabantay mo, digital na jud siya, gi-convert na niya ang analog wave, gihimo na niya ang digital jud. So inana mo gana ang analog to digital converter sa atong Arduino. So ang gigamit ani nga kuan analog to digital is successive approximation. So although lahi siya sa akong gidiscuss ganina, but same ra siya pamaagi. Same ra siya output, but lahi siya pamaagi. So mabantayan ninyo mag-change kaya but digital na jud na nga signal. So for example, ganahan ta makahiba ko pila ang digital signal nga atong gi-input, analog voltage signal nga atong gi-input is ato araning kuan gamay ato ang code. Copy ta ni. Analog voltage input is equals to, so i-multiply ra ta ni og 5 kay 5 volts man atong gigamit, then over pila ang highest binary input niya, so 1023. Then i-float na to kay para maklaro jud nato if modawat ba jud siya value between 5 to 0. So kani kay ibutang nato nga digital value so if iparanta ni so dili kay makita atong padak-an gamay. Tangan sa taning so mapansin ninyo nata sa 4 volts dapit 4.2 voltage, so which is sakto ra kay if i-swipe ta ni padong kinatom yan kay mo 5 volts ni siya. So 5 volts makita ninyo. Then ang decimal value niya is, or ang digital corresponding value niya is 1023 ang corresponding value sa 5 volts. So if i-swipe ta ni, so for example 1.44 volts, so ang corresponding value niya is 286 bit. So 286 nga digital signal. So maora na guys ang conversion sa analog to digital. So hope nakasabot ra mo. So that's all for my report.
So hi sir, hi everyone. Tonight I'll be discussing a key concept in analog to digital conversion, which is the quantization error. So throughout this presentation, I'll break down what quantization error is, its causes, and its techniques. So first, let's discuss what is quantization error. So quantization error is the inherent uncertainty in digitizing an analog value as a result of the finite resolution of the conversion process.
So quantization error depends on the number of bits in the converter along with its errors, noise, and non-linearities. So quantization error occurs due to phase differences between the input signals and the counter time base. So to explain more, quantization error happens when converting a smooth analog signal into digital form using only limited number of bits. So tungod kay dili niya ma-capture tanan small details, i-round off niya ang signal sa pinaka nearest value. That's why naay gamay nga error nga mahitabo. Mao na siya ang quantization error. Next is why does quantization error occur? So quantization error occurs because the ADC or the analog to digital converter can only represent a finite number of discrete levels, whereas the input signal is continuous. So for example, let's say you have an analog signal of 3.76 megahertz and an ADC can only measure in steps of 0.1 megahertz. When the ADC converts this signal, it will round 3.76 megahertz to the nearest step, which is 3.8 megahertz. So the small difference between the original 3.76 and the rounded 3.8 megahertz, which is 0.04 megahertz, is the quantization error. So this happens because the ADC can capture every precise value in between its defined steps. So that's the reason. Next is so this slide explains quantization error which occurs in ADC when an analog signal is converted into a digital one. So the example provided considers an ADC with a 2 voltage and 3-bit resolution. So since the 2V range is divided into 8 sub-ranges, each step in the output represents 250 millivolts. Then the graph on the slide shows a staircase pattern kaning figure beside the kuan, which reflects the ADC's transfer function. Then the steps illustrate how the analog signal is approximated by discrete values. Then the quantization error arises from the difference between the exact analog input and the nearest digital output value, resulting in a small inaccuracy. So this further explains that a smaller step height reduces the quantization error, making the conversion more accurate. So another explanation about the figure is that the x-axis, this represents the input voltage to the ADC, ranging from 0 to 2.0 volts kaning nasa ubos. Then the y-axis or the output code, this shows the corresponding digital output code in binary form that the ADC produces for each range of input value. So in the figure, we can see that an input voltage of 0V produces an output code 000. At the same time, an input voltage of 250 millivolts or the 0.25 volts produces the same output code, which is the 3 zeros. Then this is the quantization error due to the process of quantization. As the input voltage rises from 0V, the quantization error also rises from 0 LSB and reaches a maximum quantization error of 1 LSB at 250 millivolts. So this 3-bit ADC diagram is a clear example of how quantization works and why quantization error is inevitable in any analog to digital conversion. So next, so the figure above shows a quantization adjusted perfect transfer function together with an ideal transfer function. So the perfect ADC equals the ideal ADC on the exact midpoint of every step. So this slide compares an ideal ADC to a perfect ADC using their respective transfer function. So the graph shows how both ADC types handle the conversion of an analog signal to a digital one. Then the ideal ADC represented by the dashed line, kaning na ay SWOT na ideal ADC, provides an exact continuous transfer function, meaning that it would output perfectly accurate digital values with no quantization error. Then the perfect ADC, kanang iyahang atbang, represented by the staircase-like pattern, adjust the transfer function according to quantization. Each step in the staircase reflects a discrete output value corresponding to a range of analog inputs. So in a perfect ADC, the output changes only at specific intervals, which causes small deviations from the ideal function due to quantization adjustment. However, at the midpoint of each step, the output of the perfect ADC matches the ideal ADC exactly, showing how quantization leads to slight inaccuracies but maintains a consistent relationship to the analog signal. So that explains why quantization error happens. So next is the quantization error and technique. So we have three techniques in quantization error. First is the increasing the sampling rate. Second, the sample and hold circuit. And third is compounding. So increasing the sampling rate. It has been proved that for every doubling of the oversampling ratio M, we need 1/2 bit less to achieve a given signal to quantization noise ratio. So if we oversample by a factor M equals 4, we need 1 less bit to achieve a desired accuracy in representing a signal. So this technique is of little practical importance as it involves a rather high overhead. So meaning when we double the oversampling ratio denoted by M, we effectively reduce the quantization noise by spreading it over a wider frequency range. This means that less noise falls within the band of interest, improving the SQ&R. Oversampling by M equals 4. So if we oversample by a factor of 4, the SQ&R improves to the point where we can reduce the bit depth by 1 bit and still maintain the same accuracy. So for instance, if a 10-bit ADC would normally be needed, oversampling by 4 could allow us to use a 9-bit ADC to achieve the same result. So increasing the sampling rate enhances the digital signal's accuracy, reduces quantization errors, and prevent aliasing, but it would require careful balancing with system resource limitations. So, second technique is the sample and hold circuit. So this technique involves holding the analog signal at a constant value for the duration of the conversion process, which prevents the signal from changing during conversion and reducing errors due to a rapid signal changes. So how does it work? So the sample and hold circuit samples the signal at a specific point in time and holds it steady, ensuring that the ADC can accurately digitize the signal at that moment. So this technique is widely used in ADCs for signal processing in areas like audio, video, and instrumentation. So last technique is compounding. So what is companding. So this technique compresses the dynamic range of the analog signal before it is digitized and then expands it back after conversion. It helps to reduce the quantization error for signals with a large dynamic range. So again, how does it work? So by compressing large signals and expanding small ones, companding helps ensure that the ADC can capture both high and low signals with better precision. So this technique is used in telecommunication systems such as the P-law and A-law companding algorithms and voice data compression. So that would be all. Thank you for listening.
So next, I'll cover the topic of 6 types of ADC architectures and ADC performance metrics. What is ADC? So ADC stands for an analog to digital converter, and it is an electronic system that converts continuous analog signals like sound, temperature, or light into discrete digital data that computers and digital systems can process. Without ADCs, our digital devices couldn't interpret the real-world signals that we interact with every day. So basically, ang analog to digital converter or the ADC, mauni siya ang nag-turn sa continuous signals na gikan sa atuang palibot into digital form wherein the electronic devices can understand or ilang masabtan or ma-process. So this is the 6 types of ADC architectures. We have the flash ADC, the successive approximation register or the SAR ADC, the sigma delta ADC, pipeline, dual slope, and integrating ADC. First, we'll begin by discussing the flash ADC. So, flash ADC uses comparators to instantly compare the input signal to reference voltages, making it the fastest ADC type as it processes signals all at once. And its advantages include high speed, which is ideal for high frequency signals. However, it also has disadvantages such as high power consumption and being limited to lower resolutions. And flash ADCs are commonly used in applications like digital oscilloscopes, radar systems, and high-speed data acquisition. So, in summary, ang flash ADC kay nagamit ni siya og multiple nga comparators to instantly convert an analog signal into digital. And it is also the fastest ADC type, which is ideal for high-speed nga applications, but it also consumes more power and has lower resolution. Next, we have the SAR ADC, and it is a binary search algorithm, approximates each bit step by step, and it offers a balance of speed and resolution, making it suitable for applications that require precision. And its advantages includes moderate speed and efficient power usage. However, it also has disadvantages, such as not ideal for very high-speed signals. And SAR ADCs are commonly used in industrial controls, data loggers, and battery-powered devices. So, from the word approximation, so ang SAR ADC, nag-convert ni siya og signals by approximating the input voltage step by step, and it offers a balance of speed and accuracy, and it is also commonly used in medium speed high resolution applications like data acquisition. Next, we have the delta sigma delta ADC. It uses oversampling and filtering for high-resolution results, and it is slower, but the process filters noise for very accurate output. And its advantages includes high resolution, excellent noise immunity, However, it also has disadvantages such as slow, unsuitable for rapid signals. Sigma delta ADC are commonly used in audio recording, medical devices, precision measurement. So, ang sigma delta ADC mao ni siya nag-oversample sa input signal ug nagamit og digital filtering in order to achieve high accuracy. And even though nga hinay siya, but the output is very precise, and it is also ideal for audio and other low frequency nga applications. Next is the pipeline ADC. So it has sequential stages, each handling a part of the signal, and it offers an efficient balance of speed and resolution. Its advantages is it is suitable for high-speed applications needing resolution. However, it also has disadvantages such as higher latency due to a multi-stage processing, and pipeline ADCs are commonly used in applications like video processing, high-resolution imaging, and communication systems. So, ang pipeline ADC, mao ni siya nag-process sa data in stages for a high speed o high resolution nga output, and suitable po ni siya sa mga high frequency nga applications sama sa video o communication systems. Next, we have the dual slope ADC. It integrates input over time, then discharges it for conversion, making it a highly accurate, effective at noise rejection, though slower, and its advantages include high accuracy, stable in noise environment. However, it also has disadvantages such as limited speed, making it suitable for low frequency signals. And dual slope ADCs are commonly used in applications like digital multimeters and precise measurement tool. So, ang dual slope ADC kay mao ni siya nag-integrate sa input signal over a period, then measures it in order to produce a digital output. And hinay ni siya but highly accurate, and it is often used in digital multimeters. Lastly, we have the integrating ADC. It continuously integrates the analog signals for stability, making it excels in accuracy and stability but trades off speed. And its advantages include high accuracy and good and noisy environments. However, it also has disadvantages such as not suitable for fast changing signals. And integrating ADCs are commonly used in applications like environmental monitoring and precision instrumentation. So, ang integrating ADC, it measures the input signal by integrating it over a fixed time, which reduces noise and increases accuracy. So, it is best for a low speed and high accuracy measurements such as in precision instrumentation. So moving on, I'll be discussing the ADC performance metrics. So what is ADC performance metrics? So these are the criteria used to evaluate the effectiveness of an analog to digital converter, and these metrics indicate how well an ADC converts analog signals into digital form and help determine its suitability for specific applications. So in summary, ang ADC performance metrics nag-refer ni siya sa essential criteria nga gigamit in order to assess how well an analog to digital converter performs. So ADC performance matrices includes resolution, sampling rate, signal to noise ratio or the SNR, total harmonic distortion or the THD, dynamic range, and lastly, the latency. So let's begin by covering the concept of resolution. So it is the smallest detectable change in input and measured in bits, and higher resolution gives finer detail, essential for accurate digital representation. So resolution is a very important metric that defines the smallest change in input voltage that an ADC can detect, and it is usually measured in bits. And for example, an 8-bit ADC can represent 256 distinct values. So, higher resolution allows for more precise measurements, which is especially important in applications like audio processing, where subtle variations in sound need to be captured accurately. Next, we have the sampling rate. So, it is the number of samples per second and it is measured in hertz. Faster sampling rates are necessary to capture high frequency signals. So, ang sampling rate nag-indicates ni siya how frequently the ADC samples the analog signal. And the higher ang imong sampling rate means the ADC can capture rapid changes in the input signal more accurately. And important kini siya sa mga applications like digital audio o video, kung asa or where it's essential to represent fast changing signals. Next is the signal to noise ratio, or the SNR. It is the ratio of signal power to noise power, and it is measured in decibels. And a higher SNR means clear signals interpretation, important for accurate output. So, the SNR, mo ni siya ang nag-measure sa ratio of the desired signal level to the background noise. Then, a higher SNR uh, mas ma-signifies niya ang clearer signal representation, which enhances the overall performance sa imuhang ADC. And kani nga metric kay kuan kani siya, important kani siya in communication systems, kay where high SNR reduces interference and nag-ensure og better quality sa transmitted nga signal. Next is the total harmonic distortion, or the THD. It measures distortion in the signal expressed as a percentage. And low THD ensures output fidelity, critical for audio and precise applications. So, ang THD, mao ni siya ang nag-measure sa distortion, introduced by an ADC when converting an analog signal to digital. And nag-quantify ni siya og how much of the output signal is made up of harmonic frequency kumpara sa fundamental frequency sa input nga signal. And the lower ang imong THD, mas na-indicate ang mas klaro o limpyo or kanang more accurate nga representation sa imuhang signal, which is particularly important sa audio nga applications where sound fidelity is important. And for instance, high THD, if taas imong THD, it can result in mas kanang klaro nga audio nga art, mas noticeable nga audio artifact. So it can affect the quality sa imuhang music or sa imuhang voice recordings. Next, we have the dynamic range. So, it is the range of signal strengths the ADC can process, and it is also measured in decibels. High dynamic range allows ADCs to handle both weak and strong signals accurately. So, ang dynamic range kay nag-refer ni siya sa range sa imuhang input signals nga imuhang converter can accurately convert gikan sa kinagamyan hangtod sa kinadak-an, and it is also often expressed in decibels, and a wide dynamic range is essential in applications like audio recording where both soft and loud music or sounds must be captured without distortion. Lastly is the latency. So it is the delay from input signal to digital output. Low latency is crucial for real-time applications like video or communication. So, ang latency kay nag-refer ni siya time time delay from when the input signal is applied until the corresponding output is available. So, mas ubos imo latency. So, lower latency is essential for real-time applications where immediate feedback is necessary. For instance, sa like in robotics o audio processing, any delays can significantly impact performance of the user experience. So matching ADCs and metrics to applications. So if you're looking for a real-time applications, flash ADCs are ideal due to their speed and low latency. And if you're looking for a high resolution needs, Sigma Delta ADCs excel
Good
in
day everyone, my
applications like
name is Michaela
medical
Calato
imaging
and
and
I'll be the
audio
one who will
recording.
discuss
And if
the
you're looking for
noise
a
and error
average or a
in
balanced
ADC and
applications,
also the applications
SAR
and the
and
case
pipeline
studies.
ADCs
So
provide
what is
a
noise
mix
and
of
errors? So noise and
moderate to high
errors are
speed
common
and
issues that can
resolution.
affect the accuracy of analog to digital converters. So this imperfection can introduce unwanted variations or inaccuracies in digital output signal. So noise and errors daw is kana issues siya, mga issues na makaapekto sa correctness or exactness sa analog to digital converters. Next is we have the types of noise. First, we have the quantization noise. So this is inherent to ADC process when an analog signal is converted to digital. There's a loss of precision due to rounding. The smaller the step size of ADC, the less quantization noise. So for example, imagine imong i-try og measure ang height sa isa ka person using only centimeter markings. So if the person height is 172.7 cm, you would round it to 173 cm. So ang rounding is mo na siya nag-introduce sa quantization error of 0.3 centimeter. So, ang quantization error di ay is mo-occur siya when a continuous value like height is approximated by a discrete value like kanang markings sa ruler. Next is we have the thermal noise. Thermal noise is caused by a random motion of electrons in ADC circuitry. It increases with temperature. So, for example, kanang noisy radio, kanang saba kay na radio ba? So, ang kanang static na imuhang madungog, kay tungod na siya sa thermal noise sa radio circuitry. Next is we have the shot noise. Shot noise is caused by the statistical fluctuations. Fluctuation means change na siya ha, in the flow of electrical current. It's more prevalent in devices with high currents. So, next is we have flicker noise, also known as 1 over f noise. It has a frequency spectrum that decreases with increasing frequency. It's often associated with imperfections in materials. Next is we have the types of error. We have the offset error. This is the ADC to output a non-zero value when the input is 0. So, ang example is kanang scale. Timbangan na always siya mo read bitaw og 1 kilogram bisag wala siya gibutang, sa babaw. So, mo na siya ang isa ka example sa offset error. So, it means diay na ang ADC sulod sa scale is producing a non-zero output even though the input weight is 0. So next is gain error. This is a systematic error that causes the ADC to amplify or attenuate the input signal by an incorrect amount. So example ani niya is thermometer. Kanang thermometer na kanang always bitaw siyang mo read to 5 degrees higher than the actual temperature. So, isa na siya sa example sa gain error. So, it means na kanang ang EDC sulod ana sa thermometer is amplifying the input signal or the temperature by an incorrect amount. So, mo to siya nag-result siya o systematic overestimation. Next is we have the applications and the case studies. So in applications in various fields is we have medical imaging. So acquiring and processing medical images such as X-ray, MRI, and CT scans use sensors that generate analog signals based on the interaction of radiation with the body. So ADC convert these signals into digital data that computers can process to create images. So high resolution ADC are crucial for capturing detailed images of internal organs and tissues, also aiding in diagnosis and treatment. Next is we have audio recording. So processing analog audio microphones converts sound waves into electrical signals. So ADC samples these signals are at a high rate, capturing the audio information. So the quality of an audio recording depends on the ADC resolution and sampling rate. So high quality ADCs are in professional audio's equipment to capture accurate and detailed sound. Next is we have the industrial control. So monitoring and controlling industrial processes, sensor in factories and plants, measure various parameters like temperature, pressure, and flow rate. So ADC convert these analog measurements into digital data that can be processed by control system. So accurate and reliable ADC are essential for maintaining efficient and safe industrial processes. Next is we have the telecommunications. So analog signals like voice and data are converted into digital signals using ADC for transmission over digital networks. So ang ADC enables efficient and reliable communication over long distances. Next is we have the video games. So cameras in gaming console capture analog video signals. ADC convert these signals into digital data that can be processed by the game's graphic hardware. Next is we have the case studies. So case study 1 is a high resolution ADC for medical imaging. So problem is medical imaging techniques such as MRI and CT scans require high resolution ADC to capture stable variation in tissue properties. So this variation can be crucial for detecting and diagnosing diseases. So solution is a high resolution sigma delta ADC is designed with a resolution of 24 bits and a sampling rate of 1 MHz. This ADC is integrated into a medical imaging system, allowing for precise measurements of tissue and attenuation and contrast. So in challenges, we have power consumption, noise, and calibration. So power consumption, sigma delta ADC can be power hungry, especially at high resolutions. So techniques like clock gating and power saving modes are employed to reduce power consumption. So sa noise is we have thermal noise and quantization noise can be degrade the image quality. Careful circuit design and noise filtering techniques are used to minimize noise. Next is we have the calibration. The ADC must be accurately calibrated to ensure accurate measurements. So calibration techniques such as offset and gain calibration are implemented. Next is we have the case study 2, a high-speed ADC for telecommunications. So the problem is the modern telecommunication systems such as 5G wireless networks requires high-speed ADC to support high data rates. This ADC must also be energy efficient to meet the demands of mobile devices. So ang solution is a high-speed pipeline ADC is designed with a resolution of 14 bits and a sampling rate of 1 gigasample per second. This ADC is integrated into a 5G base station, enabling a high-speed data transmissions. So, we have the challenges, the speed, the power consumption, and also the matching. So, speed is pipeline ADC can be complex and difficult to design at a high speed. So, techniques like pipelining and clocking strategies are used to optimize performance. Power consumption is a high-speed ADC can consume a significant amount of power. So, power-saving techniques such as dynamic voltage, scaling, and clock gating are employed. Last is we have the matching. The analog components within the ADC must be carefully matched to ensure accurate operation. Layout techniques and processes various are considered during the design. Last is we have the case study 3, a low power ADC for IoT devices. So the problem is Internet of Things IoT devices often operate on limited power budgets. So therefore, ADC used in these devices must be very efficient. Solution is a power supply successive approximation ADC is designed with a resolution of 12 bits and the sampling rate of 100 G sampling per seconds. This ADC is integrated into an IoT sensor node, allowing for the measurement of environmental parameters such as temperature, humidity, and pressure. Also, we have the challenges. The power consumption is a successive approximation ADC can be relatively power efficient, but further optimization are needed for IoT applications. Techniques like power gating and low voltage operation are employed. Next is we have the noise can be degrade the accuracy of measurement in IoT devices. So careful circuit design and noise filtering techniques are used to minimize noise. Last is we have the integration. The ADC must be integrated with other components on a single chip to reduce size and power consumption. This requires careful consideration of layout and parasitic effects.